So we're starting Module 3, which is aligned with Chapter 3 in our textbook, Chemistry in Context.
Nuclear reactions occurring in the Sun provide energy to the planets surrounding it. Electromagnetic radiation released from these intense reactions travels many miles from the Sun, passes through the Earth's atmosphere, and provides us with energy. There are different regions of the electromagnetic spectrum. Some are essential for life, while others are hazardous to our health. But how much exposure is enough, and how much is too much? Can too much exposure to the sun's radiation damage your health? What methods of sun protection are most effective? Are there chemistry products that help protect us from overexposure? Do chemical reactions in the Earth's atmosphere protect us from harmful radiation? In this chapter, we will learn about the sun's radiation and how chemistry can protect us from overexposure to the sun's harmful rays.
That video, there's a link to it in today's additional review videos. It's important to understand both the positive and negative implications of sun's radiation on Earth. So positive, suntan, vitamin D, which is a vitamin you can buy and take, or you can go outside for 10 minutes a day of sunshine and get vitamin D production in your skin, begins at the level of your skin, which we'll get into, vitamin D for free if you don't want to buy the vitamin D, which is a necessary vitamin for your body. Plants, we know, absorb sunlight and create not just food, but also oxygen for us, for humans. And we also know that sunlight, the energy from the sun, maintains Earth's temperature. Negative, well, sunburn. There's also skin aging and skin cancer. And a side product of the maintaining of Earth's temperature is climate change and global warming, which we will be getting into in Chapter 4. But some of the questions that are covered in this chapter, we'll look at radiation from the sun and the link between sun exposure and skin cancer, and how Earth's atmosphere naturally protects us. Radiation, as far as sunlight and electromagnetic radiation, so electromagnetic or EM radiation for short, is not radiation that you might be thinking of as dangerous and causes cancer. Electromagnetic radiation, which is the majority of radiation that we have in our daily lives, including coming from sunlight, electromagnetic radiation is any wave of energy, and this is called electromagnetic because it can be electric or magnetic, but this is any energy that radiates from a source, so it's called radiation for that purpose because it radiates, it comes out from a central source and it moves outward. So it radiates from a source like sun coming from the sun source, or microwaves. Those radiate out from the microwave source, or light, even a light bulb. So radiating outward as a wave, and these are called, they're waves of energy. And sunlight is energy from the sun. It contains not only the light we can see, but it also contains heat energy that we can feel, and also UV, ultraviolet energy, UV, that we cannot see, we cannot feel, but we must protect ourselves from. And one thing we'll get into is how Earth's atmosphere protects us from the harmful effects of UV radiation. And this week's discussion topic is harmful UV radiation that we can use to protect ourselves from viruses like the coronavirus. So you'll see that discussion topic. Electromagnetic radiation are all these types of energy, all of which radiate as waves. They're found throughout the universe and definitely here on Earth. So there's ultraviolet, UV, X-rays, gamma rays. These are higher energy. They are dangerous, and we'll talk about how you protect yourselves from higher energy waves, which include UV, X-rays, and gamma rays. But then these are all lower energy. Visible light, what you can see the rainbow of colors, Roy G. Biv, standing for red, orange, yellow, green, blue, indigo, and violet, visible light. And there's infrared, that's heat energy, IR. And there's microwaves. And how many of you guys are afraid of standing in front of a microwave? Or maybe your parents are, your grandparents. Well, microwaves, don't be afraid of standing in front of a microwave. Definitely not after chapter 3, because microwaves are low energy and do not do anything but heat your food. We'll get into exactly how microwaves work in this chapter, but more in chapter 10. Properties of waves include its wavelength and frequency. And we'll be talking about these both in general and as well as using wavelength and frequency in calculations, beginning with lab this week, and we'll be working on that through till next week. So wavelength is represented by this symbol. This is an upside down Y, but it's called lambda in the Greek alphabet. And wavelength is the distance that's traveled from peak to peak of a wave. So a wave is a continuous wave, and I'll show you this here. This is a continuous wave. It's continuing in both directions infinitely, and the distance from the peak of one of these to the peak of the next one, that's one wavelength. It can be peak to peak. Frequency is how many of these waves, so here's a single wave, here's another single wave, here's another single wave, in this whole series, how many of these waves pass through a fixed point, so choose a point like right here, and count how many of these waves pass through in 1 second. So frequency is the symbol, which is kind of like a cursive V. It's called nu in the Greek alphabet, and it represents the number of waves that pass through a point in 1 second. So let's talk about these. These are symbols you're going to have to get used to, because when you're looking for an equation to calculate wavelength or frequency, they're not words. You're going to be looking for the symbols in using equations, and you need to get used to the symbol for wavelength, as well as the units for wavelength are going to be meters, associated with a metric prefix like nanometers or millimeter. Frequency also has this Greek symbol, and this is units which you'll recognize when they're given a problem. Frequency is blah 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 because of the units, which are 1 over s, that's one per second, or how many cycles per second, or also shown as s to the -1, which means 1 over s, or also using this unit which is called which is hertz or hz. So this is frequency also, which has very often metric prefix associated with it, like a gigahertz or a megahertz. So wavelength and frequency are inversely proportional. If one is high, the other is low. So you can see if you have a big distance, a high amount, or a long wavelength, you don't have very many of these waves passing through in 1 second. That's a high wavelength and a low frequency. If you have a wave like this, this is a low wavelength, a short wavelength, less distance between the peaks, and that means you have more of these waves passing through in 1 second. So low wavelength, higher frequency.